In this video, we'll be talking about the electric potential energy of a charged particle in this space between two oppositely charged parallel plates. So we'll just work through the questions together and follow along in your notes. So number one, where would it have the most electric potential energy and where would it have the least electric potential energy? Well, if you think about a positively charged particle in this space, and you can think of it at these different positions, A, B, and C, if you put it here, right next to the negative plate, it's not going to go anywhere. It's almost like a ball sitting on the ground. It can't fall anywhere. It's already at its sort of lowest position. If you put it here, however, it's going to want to go this way. Naturally, it's going to go that way. So this is going to be the place of highest electric potential energy, near the positive plate, and then near the negative plate would be the place of the least electric potential energy. And another way to see that is if you're to take this positive particle, you would have to exert a force over a distance to get it over here. That's just the same as if you want to lift a ball into the air. You have to exert a force to oppose the force of gravity to get it lifted up. So it's very similar here. You're doing work, and that work is transferring energy into the system and increasing the electric potential energy. So it would have the most electric potential energy at C, and it would have the least electric potential energy at A. Number two, what happens to its electric potential energy if it changes position from A to C? And as we just mentioned, it is not going to do that on its own. You would have to have an external force to move it over there. But if that was done, that's going to increase its electric potential energy. And if it changed position from C to A, that would be a decrease in electric potential energy. Just as if a ball is dropped, as it falls to the earth, it decreases its electric potential energy. It decreases its gravitational potential energy. Number three, draw the electric field between the plates. So we know that electric field lines show the direction that the force would be on a positive test particle if you put one there. So to think about which way the electric field would be, just imagine that you have a positive test charge here and think about what the direction of the force would be. You can see the direction is going to be away from the positive plate and toward the negative plate. So this would be the direction of the force to the left. So that tells us the direction of the field. And then we also learned that in the area between oppositely charged parallel plates, the electric field has a uniform magnitude. It has a constant value. And we show that by making our electric field lines equally spaced. So I'm going to try to draw these lines equally spaced from each other. And be sure when you're doing your drawing that they look equally spaced. If they don't, make a note saying these are equally spaced, or should be. Okay, 4. What is the force on the particle at A, B, and C? And I want the force in terms of the charge of the particle and the value of the electric field. We learned already that the definition of the electric field is the ratio of the electric force divided by the charge of the particle. And it can be really useful to rearrange this because you can use this to find the force on a charged particle in an electric field. So the force on a charged particle in an electric field is the charge of the particle times the electric field. And we did some of these types of examples in class, or with the chart, where we knew the electric field and we knew the charge and we calculated the force. And that force is always going to be to the left at all places. And notice that it has a constant value. The force here on the particle is exactly the same as the force here. It's not a bigger force when it's near the positive plate because the electric field always has the same value and the charge always has the same value. So the force is constant. And that's also really similar to dropping a ball at the surface of the earth, right? The force of gravity at the surface of the earth is pretty much constant, m times g. And so you end up with a constant acceleration, and this particle is going to have a constant acceleration as it moves across this space. Okay, what is the equation for calculating electric potential energy? So our system for doing this is going to be the parallel plates and the charged particle Q. And here's our scenario. You exert a force to move the positively charged particle from A to C at a constant velocity, which means that the kinetic energy is not changing. So we're going to draw a little LOL diagram here, and then we'll be able to derive the equation using this process. So our system is the parallel plates and the particle. And this is going to be at A, and this is at C. Now, in order to move the particle, we would have to exert a force on it, because it's already experiencing a force in this direction with magnitude QE. Just like a ball, if you want to lift a ball into the air, it's experiencing a force of gravity downward, so you have to balance that force with an upward force of your hand if you want to lift that ball. Okay? This is the same thing. If we want to move this charged particle from the negative plate to the positive plate, we need to have an external force. I'm just going to call this the force of me. And I have to balance that electric force to move it with a constant velocity over here. I need balanced forces in order to move it with a constant velocity. So I'm going to be doing work on it because I am an external force. I'm not part of the system. So let's fill out the diagram. At A, let's just suppose it's moving with some velocity. So we have some kinetic energy. And it's starting here at the negative plate. So it doesn't have any electric potential energy at A. Then I'm going to do work, and let's just say I do 3 units of work in moving it from A to C. So then at C, it'll still have the same kinetic energy because I was only just balancing the force. And now at C, it has electric potential energy. So that work I did transferred that energy into the system, and now it has electric potential energy. So let's write our energy conservation equation. The energy at A plus the transfers, which in this case put energy in, equals the energy at C. And at A we had some amount of kinetic energy, and then we had work that was done. And then that equaled the same amount of kinetic energy as before, plus this electric potential energy. Well, the kinetic energies are the same, so they go away. And now the question is, how much work was done? If we can calculate this, then we will know an equation for the electric potential energy. Or rather, if we can write an expression for this in terms of our variables, that gives us an equation. So this is how we derive equations for electric potential energy and other potential energies. So if you remember how we calculate work, it's the force times the displacement times the cosine of the angle between those two things. The force in this case is my force, and my force is equal to the electric force. So the magnitude of the force is Q times E, because my force equals that one. So Q times E, and the distance is going to be the entire distance between the plates. And the angle between the displacement and the force. So my force was to the right, the displacement was also to the right. So those are in the same direction, they're parallel. So the angle would be 0. And remember that the cosine of 0 is 1. So our result for electric potential energy is the charge times the electric field times the position in that between those plates. And it's important to know what to put in for these different things. For Q, you need to put in the charge, and you need to put it in with its sign. So if it's negative, be sure you put in the negative sign. E is just the magnitude of the electric field. So don't put any positives or negatives for that. And D is the position in the field, and that is from the negative plate. So we are always going to set our D-axis going this way with the 0 value right here at the negative plate. So that's D equals 0, and then positive D values here. Okay, let's do an example of how this works. Two parallel plates with opposite charge are separated by 4 meters and have an electric field of 100 newtons per coulomb between them. Find the electric potential energy of a particle with charge positive 2 coulombs when it is at the negative plate. So that is a position of 0. So D equals 0. The electric field is 100. The charge is positive 2 coulombs. So we can calculate electric potential energy using our equation, Q times E times D, positive 2 coulombs, electric field was 100 newtons per coulomb, and the position is 0. So we can see that we have an electric potential energy of 0 joules at the negative plate. And that makes sense because it's kind of like a ball at ground level. If ground level is your 0 height, then the ball has 0 potential energy there. Part B, find the electric potential energy of that same particle when it is at the positive plate. So now the position is 4 meters. Our other variables are the same. And we can calculate the electric potential energy. Q times E times D, positive 2 coulombs times 100 newtons per coulomb for the electric field times a position of 4 meters, and that gives us 800 Newton meters. Now we're talking about energy here. Do you remember what a Newton meter is equivalent to? There's another name for that unit. You might remember it from work, because work is a force times a distance, which is actually a unit for energy. So this is 800 joules, and that's a positive energy. So you can see as this positive particle, if it were to go from A to C, it would be going from 0 joules to 800 joules. That would be an increase in potential energy, so that makes sense. You always want to check your results and see if they make sense. Okay, example 2. Let's apply this now to a situation where a particle changes position. A proton with charge 1.6 times 10 to the negative 19 coulombs is released from the positive plate. The distance between the plates is 0.05 and the electric field is 480. Find its speed when it reaches the negative plate. So as we talked about, a particle released here is going to have a force on it, and that is a constant force, and it's going to have a constant acceleration going this way. So our two positions are, it's going from C to A. So at C, it has, let's see, it's not moving, so no kinetic energy. We're not dealing with any gravitational forces with these kinds of situations. But we do have electric potential energy at C. So I'm going to put a little bar for that. Now as it moves from C to A, there are no external forces, so there are no transfers. And I should put my system in here. We have the proton and the charged plates as the system. Now at A, it has 0 electric potential energy, but now it has kinetic energy. All of the energy that was stored as electric is now stored as kinetic. So our energy conservation equation would be the energy at C equals the energy at A. And at C we had our electric potential energy, and at A we have our kinetic energy. This is Q times E times D, and this is 1/2 mv squared, which is familiar. Now we can substitute what we know. So 1.6 times 10 to the negative 19 coulombs is the charge. The electric field is 480. And the position at this point at C is 0.05 meters. Remember that the position is measured from the negative plate. So if the distance between the plates is 0.05, then the position at the positive plate is 0.05 meters. And then 1/2 times the mass. I'm running out of room here. The mass is 1.6 times 10 to the negative 27 kilograms. And the speed is what we're looking for. So now calculating that. (1.6 times 10 to the negative 19 times 480 times 0.05 times 2, because I need to multiply both sides by 2, and divided by 1.6 times 10 to the negative 27. And then I need to take the square root of that. So we get 6.9 times 10 to the 4 meters per second for the speed. Okay, example 3. This will prepare us for dealing with objects that have a negative charge between the plates. So this is an example with a gravitational potential energy, but bear with me, it will prepare you for what comes next. Okay, example 3. A ball is dropped into a hole that has a depth d. So what we're going to look at here is two different places where we could put our y equals 0. Usually we put y equals 0 at the lowest point, but in this situation we want to look at what happens if we put it at the lowest point and what happens if we put it at the top of the cliff. So let's work this out. In both situations, the system is going to be the ball and the earth. And the ball's just going to be dropped. Now, if y equals 0 at the bottom of the hole, then at point A, when it's dropped, it would have gravitational potential energy. So let's put 2 units of gravitational potential energy. And then it's going to fall because of the force of gravity, which is an internal force to the system. So we have no external transfers. And at point B, it's going to have kinetic energy. So our energy conservation equation would be energy at A plus no transfers equals the energy at B. We would have mg times positive d, because that's the height, equals 1/2 mv squared. So that's pretty familiar from what we've done previously. Now, if y equals 0 at the ground level, what happens? Well, in that case, at A, it has no gravitational potential energy because it has no height. This is the 0 level. So no gravitational potential, it's not moving, so we have 0 energy here to start with. Now what about at point B? At point B, now it has a height, you could say, of negative d. So it has decreased its gravitational potential energy. So the gravitational potential energy is lower than it was before, it's decreased, and has a negative height, which means we actually have a negative gravitational potential energy. And it's moving, so we have kinetic energy. And just as in this first situation, however much the gravitational potential energy decreases, that's how much the kinetic energy will increase. That's where that kinetic energy came from. So in the first example, when y equals 0 at the bottom of the hole, the gravitational potential energy decreased by 2 units and the kinetic energy increased by 2. The same thing is happening here. Here we went from some positive number to 0 for the gravitational potential. Here we're going from 0 to a negative number, but it's still a decrease of 2 units. And this is an increase of 2 units. It's just a little weird because it's hard to think about what a negative gravitational potential energy means, but just realize it's all a little accounting system. Just relative to this as the 0, this is negative. So energy at A equals energy at B, and so now our gravitational potential energy, at A we have no energy, so 0 And then at B, we have mg times negative d, so we have a negative gravitational potential energy, plus the kinetic energy. And if you see, if we added this to both sides of the equation, we're right back at what we had before with the other choice. So they're equivalent ways of doing it. And here's why this is useful. Because it's very similar to what happens when we are working with a negatively charged particle between the plates. So let's think these through. Where does it have the most electric potential energy? So here's a little negatively charged particle. Here's another one. Would it have the most potential energy here, close to the negative plate, or here, close to the positive plate? Well, when it's close to the positive plate, it's not going to go anywhere. It's kind of done, like when you drop a ball and it lands on the ground. So this is going to be the lowest, and this is going to be the highest for the electric potential energy. So it has the most at A, and it has the least at C. So what happens to its electric potential energy if it changes position from A to C? Then it's going from a high value to a low value. So it's decreasing. What if it changes position from C to A? Well, you can see that's going to take some effort, right? Because it's naturally being pushed this way. That's the direction of the force on it. So you're going to have to do some work, exert a force, to push it over here. And that's going to increase its electric potential energy. Question 3. We defined our zero level of electric potential energy to be zero at the negative plate. And that's because this is our zero position, and electric potential energy is Q times E times D. So if it's here, by definition, it has 0 joules of potential energy. So how is it possible for it to have less, a lower value over here? If this is 0, what values could it have that are lower than 0? It could have negative values. And that's actually what happens. It has 0 potential energy here, and as you go this way, the electric potential energy values become more and more negative. So they are decreasing. That'll take a little bit of getting used to. So it can decrease by becoming negative. And then draw the electric field between the plates. So it's the same setup as before, so equally spaced lines. What is the force on the particle at A, B, and C? So same thing as before, the electric force is the charge times the electric field. And you have to think it through to get the direction here. The charge is negative, which means it is not going to have a force in the direction of the electric field line. It's going to be opposite the electric field lines. And so the force would be to the right. What are the signs of each variable? So when we are calculating electric potential energy, for a negatively charged particle, this is going to be negative. The charge will be negative. You'll be putting a negative number in there. Electric field is a magnitude, so that's just a positive number. And position, so that's where it is also a positive number. So you can see this is going to end up giving you a negative value, except for when D is 0. Okay, let's just apply this now so you can see how it works. Example 4. 2 parallel plates with opposite charge are separated by 4 meters and have an electric field of 100 newtons per coulomb between them. Find the electric potential energy of a particle with charge -2 when it is at the negative plate. So electric potential energy is Q times E times D. It is always a good idea to list your variables. It helps you dissect the question and figure out what you know before you start doing algebra. So the electric field is 100, and the position, it's at the negative plate. So remember, your position axis will always look like this with the 0 at the negative plate. So the position is 0. Well, no matter what these are, if the position is 0, we're going to have 0 joules. Okay? So the the negative particle has 0 joules of potential energy at the negative plate. Now what about when it's at the positive plate? The only thing that's going to change now is that the position will be however far apart the plates are, 4 meters. So the charge is -2 coulombs. Make sure you put in that negative sign. The electric field is 100, and the position is 4, and that gives us -800 joules. Okay, and let's see if this makes sense. 0 joules, -800 joules. So it should decrease in potential energy as it goes this way, and sure enough it did. It went from 0 joules to -800, so that's a decrease in electric potential energy. And to finish up, we have an example with a negatively charged particle which is going to move between the plates. The mass is 9.11 times 10 to the negative 31, and the spacing of the plates is 0.05. Now be careful, this is the spacing of the plates, which may or may not be the position of the particle. So maybe I almost think maybe we should call that a capital D, because that's a very special distance. Okay, find its speed when it reaches the positive plate. So it sounds to me like it's starting at position A, at A, and then the positive plate is C. So we're looking at from A to C. And there are no external forces, so the energy at A should be equal to the energy at C. And we have the electron in our system and the plates. And there are no transfers. Okay, now energy at A. At A, the electron is at the negative plate. Any particle at the negative plate has 0 joules of electric potential energy. So, and it's not moving and doesn't have any height above the ground. We're not dealing with any gravitational forces here. There's no stretch spring, so we have no energy stored at A because we have set our 0 position at the negative plate. It's because of our choice of 0. Then at C, what has happened? At C, remember, a negatively charged particle will have a negative potential energy because from A to C, it has to decrease its electric potential energy. So it's going to have some kind of negative electric potential energy. And we know it's moving, so it's going to have some kind of positive kinetic energy. And remember, the decrease in electric potential energy is going to equal the increase in kinetic energy. Okay, so let's solve this. We have the energy at A equals the energy at C. We have 0 energy at A. What do we have at C? We have electric potential energy, and we have kinetic energy. And now we can put in our values. -1.6 times 10 to the negative 19 times 480 newtons per coulomb. And this would be the position at C, which is at the positive plate, so that is 0.05. So always be sure you think that through. Plus 1/2 times the mass, which is 9.11 times 10 to the negative 31 kilograms, times v squared. And go ahead and input that into your calculator. Actually, before I input it into my calculator, at least the whole thing, I'm going to just calculate this part right here, which comes out to be negative 3.84 times 10 to the negative 18 plus 1/2 times this thing. And so then we can add this to both sides. 3.84 times 10 to the negative 18 equals 1/2 times the mass times v squared. And then solve for v and make sure that you get 2.9 times 10 to the 6 meters per second. Okay, so it increased in speed because as it moved from here to here, it had a decrease in electric potential energy and an increase in kinetic energy.